in the last webinar. So again, welcome to Simulation Analytics. My name is Durrell Rittenberg, and I'm joined today by Scott Imlay.
Good morning, everyone.
And we're very excited to have an opportunity to share with you some of the work we've been doing around providing solutions for simulation analytics. Let's quickly review what it is that we're going to talk about today. So we'll talk quickly about what's driving the market towards the need for simulation analytics. We'll review some of the things we talked about last webinar, which is what does simulation analytics really mean. And then we'll actually look at a couple of simulation projects using Tecplot Chorus just to show you how one can actually leverage some of these techniques to evaluate complex systems. And there'll be plenty of time for Q&A, so if you have questions, feel free to either type them in, or when we get into Q&A, you're more than welcome to raise your hand and we can unmute you and you can ask a question live. And just a quick note for those of you who are interested, we do have a white paper available that you can download. It's on the Chorus site, so it's www.tecplot.com/chorus, and that's a white paper on simulation analytics. Scott Imlay actually was the author of that. Mm-hmm. And also, if you're interested, you can take a look at the product as well just by going to the same page, and we'll talk about that more later. So well, let's start, Scott, with a quick review of what is simulation analytics.
Well, first of all, it's a combination of, it's the application of analytics to simulations, and simulations meaning computational simulations generally. So the analytics is visualization, data management, statistics, data mining, all being applied to this collection of data sets that you get from a set of simulations for a project.
Mm-hmm. Now, is it limited to simulation? I know that we talk about that a little bit, but can you apply the same strategy to wind tunnel test data or other test data as well?
Absolutely, yeah. I mean, it isn't limited to simulations, but that I think is the unique nature of it, is that it has a lot of capabilities that really make it valuable for simulations.
Mm-hmm. So how's that different, I guess, from just simple business analytics?
Well, the major difference is the nature of the data. So your original analytics are applied to a collection of data that is like, financial data or something. But in the simulations, you actually have two levels of data. You have your field data that come out of the actual calculations. So that would be things like pressure and temperature, velocities. And then you have a collection of data that is summary data, if you will, metadata, that's is things like integrated forces and moments, or it could be other things like perhaps a maximum temperature or something like that in your field.
And of course, it's not limited to that. It could be descriptors. Oftentimes, anything from what code was used.
Absolutely, it's the inputs as well as the results. Sure.
So in that context, simulation analytics, as we've been talking about here, is really the marriage of the business analytics, which are pretty mature at this point in terms of the analytical approaches to subsetting n-dimensional data, tied to the physics or field data. And one thing that we're running into quite often is that there isn't a convenient way to manage hundreds of simulations or even tens of simulations. So having kind of something that you can also manage a project is really what simulation analytics provides. It's the analytics, the visualization, and the management of the project.
Mm-hmm. Okay, so as an engineer, you really, working with these simulations, you really have a range of things you're trying to do. First, you need to manage the data. Now, this is a major deal because this could be a large amount of data that you're generating from these simulations. And, there's been, for instance, not too long ago at a conference, there was a quote that 30% of the engineer's time was spent just managing the data, trying to keep track of where it is or find it, 6 months later or whatever. So that is, sort of the basic thing you have to do. And then then you need to, when you're analyzing the data, you need to identify trends and anomalies and unexpected behavior in the metadata. So this is the metadata level stuff. And also you need to dive down into your field data when you find these trends and anomalies and try to understand what's going on. So that's sort of the third level of things. So, and then, for analyzing the metadata, you're using visualization and statistical analysis, and also surrogate modeling, which I will talk about a little more in a second.
Mm-hmm. So then I guess there's a number of things. The three main areas that we're seeing the need for simulation analytics: sensitivity, probabilistic analysis, and robust design and reliability-based design.
Sure.
Maybe it's worth just spending a moment on kind of what are those approaches and how does simulation analytics kind of fit together?
Sure. This is all based on the surrogate model, which is really a representation of the data between your points. So this could be a fit of a function, or it could be a more complicated model like a Kriging model, statistical interpolating technique between the paint points in your metadata space, your n-dimensional space. And so in that space, you might want to get an idea for the sensitivity of your outputs, your results, to various inputs. This is common, sometimes in weather forecasting, for instance. That's more of the probabilistic, which is the next one. But in weather forecasting, a lot of times, for instance, you have an extreme sensitivity to initial conditions. So you might want to actually run a bunch of cases with slightly perturbed initial conditions, and then you want to see evaluate the result. So how much does a slight change in initial condition impact your weather 3 days from now, for instance? And then the probabilistic analysis would take that information and actually build a model, say, based on the Monte Carlo simulation, build a probabilistic model of just how likely something is to occur. Mm-hmm. Robust design is related to that in that well, this was originated by Toyota, and in their case, for instance, they wanted to have cars that would start no matter what. And so you're not just trying to design for a point or even a few points. You're trying to design for a base ability of your vehicle. And in that case, they would say, I want it to start whether it has a spark plug or it's 10 years old, or no, it doesn't matter. Mm-hmm. And so they would go through a large number of simulations and just looking to see if it worked in all of those cases.
So in that context, let's just switch gears a little bit, and we'll talk about, if you just look at the mechanics for a moment of what you'd want to do with a system. So say you were trying to predict performance or look at a probabilistic design study. 9 times out of 10, what you're going to be doing is running in batch a number of simulations across a series of initial conditions. And you generate, in effect, this asset of solutions, and they could be test, they could be solution files, this could be field data, could be convergence history. You may, in fact, have some base images that are created. And ultimately, going from this, asset of information, the data, the images, into a project is really where we see a lot of people struggling. And in fact, in speaking with a group recently, there was an engineer who said that they were able to kind of consolidate and get to the information that they had access to initially. In one way, they just never looked at it. They had no way. They said, hey, it took infinitely too much time to look at all the results we had. In using a simulation analytics approach, they were actually able to bring in that information and go, hey, wow, I can actually see what I couldn't see before. So we're going to walk through an example of this, and we're going to show that you can start with just an aggregate of data, and we're going to actually walk through 2 use cases that will help illustrate how easy it is really to start at a reasonable start point being just the raw solution files, and to create a series of reduced subset field data, some plots that we can actually do both qualitative and quantitative analysis of. So we're going to go and show you how you can actually use this approach to create an asset and then analyze the results of that asset, and ultimately show you how it's something that's relatively easy to do. Because one of the things we're hearing in the market is that it's relatively easy to generate solutions now. Most codes can be parallelized, and you could run 2,000 initial conditions without any problem, given the computational resources most organizations have now. That's really 200, 300 results on the weekend isn't really a big deal.
No, but actually going through and looking at all of those results is a big deal. It takes a while to load the data and examine it all. So that's one of the main values in this sort of approach.
And it's interesting. And meeting with a turbo manufacturer that I met last week, in fact, we sat down and we were talking about the work that they do. And one thing they pointed out is they don't look at it at this point because they just said,
yeah,
I've got too much results. They look at the derived quantities and say, all right, that'll likely work, and then they have to move on just because they don't have the time. So we're going to show you how you can do both qualitative and quantitative differences of created results, and we'll also talk about how you can analyze the derived quantities. And so at this point, we're going to shift into Tecplot Chorus, which is an application we've developed to address simulation analytics. So I'm going to see if I can do this in a savvy way or not. Okay. This is the Tecplot Chorus environment, and one thing that you're looking at here is just a series of solution files. We actually are looking at a time-dependent solution where each one of these is a time step. And if I zoom in just a little bit so you can see this, we're actually looking at 5 blade configurations over, it looks like 11 representative time steps. And the idea here is you want to understand, okay, based on these different blade configurations, if we were to look, say, at just blade 1, we want to understand, what's actually going on here. And this is the initial base case. So if I just take a look at the images we have here, and I'll zoom in a tad. So this is actually just one time step. And if I you can quickly go through and look at each representative time step. And one thing to point out as I walk through here, it's the vortex shedding. And the authors were trying to optimize, and this is actually a use case that was courtesy of the folks at Pointwise. We did a webinar on this very case where they were trying to maximize lift on these blades. And one of the things that you can see is that here's a good example of it here, that in this area actually you're starting to see a formation of vortices on the leading edge, and that's actually decreasing the performance.
Right. Yeah. You want to avoid the large scale separation as much as possible.
So this was the initial design, and if we go now and take a look at the optimized design, which I believe is it's either 3 or 5, but let's go ahead and take a look at 4, for example. We can do the same analysis. Now we're going to look and see, effectively what the new vortex shedding behavior is going to be. Same kind of thing. I can now just dive in, and you're starting to look at it. So there's this tie-in. Now if I say, God, yeah, that doesn't look right, that's kind of the opportunity at this point to say, let's go ahead and dive in and take a look at the actual physics of this system. So we're going to pop in now and actually dive in to do some physics visualization. And here's the simulation that we're talking about, and you can kind of dive in a bit. And I can say, okay, well, what's really going on there? I might want to go in and change my contours so I can resolve some of the fine structure. If I say, oh, that looks good, and I can also, just to make sure, I can also figure out what time step, what file name, all the things that might be interesting. Okay, I can then say, all right, well, let's do some comparisons. So at time step 0, let's see what this looks like relative to, say, time step 3, for example. So having the ability to go, yeah, I'll grab these two now, and I can view the same data and really kind of do a qualitative comparison. So we'll go back over here, and you can see now that I have these 2 linked solutions. I can kind of dive in a little bit. And now you can kind of see the difference between these 2 time steps. And it's just an easy way to kind of evaluate. We're looking at 55 plus simulations. Another thing you may want to do is just say, well, at a given time step, what's the difference between my different designs? Mm-hmm. So in this context, if we view the data that we're looking at here, and one thing that we can do is just show the labels of, say, the total pressure on the blade, the time step, and which blade it is. And now if I just say, hey, here's my base blade set, and these are each optimized generation, I can then look at a very quick difference. And now I'm looking at a qualitative difference based on the images that are shown. Now, one of the cool things about this is that if the grids aren't the same, or even if the geometries are different, you can do a pixel difference very easily.
Yeah, exactly. And you know, this is really critical to be able to do these comparisons rapidly like this. And it's one of the problems with the current post-processing techniques. It just would take forever to go through a large number of cases in this manner.
And so we'll apply a little more of the analytics now. So what we're looking at is the total integrated pressure on the three blades over time. And one of the things we want to do, of course, is we're looking to maximize this result. And using this strategy, we can apply two things. One, we'll go ahead and use a simple surrogate model, which is a quadratic response surface. And that's really just going to give us the average pressure. And we'll go ahead and turn that on so you can see it for each blade. And then having the ability to use filtering to go through and look at each individual blade and walk through. So you can see in this context, this is in fact the optimal blade design, but you can see what the relative differences are from the base case to the optimized design.
Yeah, this is a fairly simple technique. It only has a couple of or a few variables, but the filtering is a very powerful exploration tool, and it'll come in, I'm sure, again as we go through this this webinar. But it's one of the dominant tools we use to really analyze the data and isolate various things. The other thing you'll notice is if you look at the left, one of the things that the filters have is a histogram representing the actual distribution of those variables throughout all your cases. And that can be quite valuable as well in helping you get an idea of where most of your data is.
And there's also, to go back to that tie-in, Scott, it's if I wanted to know, okay, well, this seems like a pretty high value, let's take a look quick at the image. So here are the images I have for that solution. And, you know, it's a quick way to dive in and go, okay, well, is it commensurate with what I thought? Is it consistent with my engineering intuition as to what's going on with the system at this point?
Yeah, basically we're looking for some level of solution quality analysis, right?
Right.
Intuition is part of that, but you need to really be able to dive in and convince yourself that this solution is good.
So this is kind of how one works with a project that's already been created. What I thought we'd do is show you what happens when you start really at time zero. You're going to have a bunch of solution files, and we're going to use a case that's kind of fun to look at, which is a case that was used to validate a model that might be used with the EPA. So we'll create a completely new project. We'll get rid of all these results. Now, the way that we've been managing data up to this point is we provide two mechanisms. One is a SQLite file, very flat, links to images, links to data. We also have the ability to use a more enterprise-level MySQL-based, which is more, it's really, well, it is a SQL-based database. And for this example, it really isn't all that important, so I'll just use SQLite. And I guess it really doesn't matter what we call it either, so call it Plume, even spell it correctly. And we're going to call this project SO2, I'm using, there we go. And this is really for EPA. So the idea is that we'll go ahead and look at what the files look like here. We're going to just quickly, so we have about 16 solutions, and each one of these solutions that I show you here, you can see that the initial conditions, the prevailing wind conditions, and the amount of a contaminant are in the actual name of the file. And you can see there's 16 solutions here, and we actually have some additional data files here as well. And I'm going to go ahead and just quickly show you that we can just aggregate the results. So one of the things that was done during this simulation was that when the simulation completed, it dumped out a bunch of derived quantities. And what these quantities are just the derived amount of SO2 gas at 75 meters from the point source, 50 meters from point source, 25 meters from point source, and then at different elevations from 5 meters to 100 meters. And then there was one additional measure, but it's probably not all that important. So this is our start point. We have a bunch of files, and we have some derived quantities. And we're going to go ahead and bring those in using just a simple CSV file, which we'll browse to quickly. And this is the output from the integration. And it doesn't just asking the directory. So we're going to point it to and say, yeah, okay, there's a file name in there, and we'll call this raw data. And most of this, it doesn't know whether or not these are initial conditions or whether or not they're derived quantities, and we'll just let it know that, in fact, the prevailing winds and SO2 concentration are derived quantities.
Right.
Or, I'm sorry.
Are the independent variables, right. Independent being, you know, what is basically the input variables, as you said.
Right. So with the tool, it's going to go through, and it's brought it in. You can see that it brought in the 16 cases. If I right-click here, you see there's nothing to it yet. There's no images, but the derived quantities are there. So if I wanted to look quickly at the design space here, and if I look at, say, the northeasterly winds as a function of SO2, and look at, say, the integrated amount of SO2 downwind, we can rotate this around real quick, and you can see, so these are my derived quantities, and that's kind of nice because it does look that as we increase SO2 concentration, there doesn't seem to be too much variability, at least with northeasterly winds. Just a quick assessment of what's going on with the system.
Now this plot shows all of the cases. Now there's only two variables on the independent variables, NE and SO2, but all of the cases are shown. If you want to show one if you just want to show one value of the third dimension, you can do that with the filters on the left.
Right. So if I wanted to just look at a given southeasterly wind, I'll go to a single value and just select 5 meters per second. So the next thing I'm going to do, though, is I really want to understand what's going on with the system, and I'm going to start by just popping open one of the solution files, and we'll go ahead and start with taking a look at the data, and I'll just make it look the way I want, which you can see here. This is absolutely just a test case. It was more to show the EPA what's possible and perhaps how CFD might play a role in validating manufacturing designs. So this is really just a test case. The real case that they ended up running was much more sophisticated than this and looked over a much wider topography. So, yeah. But for this example, I think this is fine.
And these are basically buildings, right? In it.
These are buildings, and we'll go ahead and just, as you might do with any one analyses, we'll go ahead and look at a slice, and we're not so interested in the fluid dynamics per se. We're more interested in the SO2 concentration, so we'll just look at that SO2 concentration. And you can see this is for a somewhat low concentration of SO2 gas, so we're going to need to add a couple of contour levels here just so that we can see even those very low concentrations of SO2 gas. So this is actually looks like a reasonable base image, and we're going to take advantage of this being our base image by going to make sure that it's at a reasonable elevation. Say, perfect. And I'm going to save it as a template. So in principle, you can then say this is a base image. And now that I have my base image saved, I'll go back into Chorus. I'm going to grab all my results, and I'm going to go ahead and create some images, in this case plots, using my base image style, the one that I just created, and I'll just call these base image. And I'm going to hit go. And what's going to happen is now my tool is actually going to go through and run in the background, and it's going to start creating images. So if you see here, I'm actually running a batch job in the background. So I'll close this, and while it's doing that, let's take a look at a given set of conditions. Let's look at 4 sets of data, and we'll bring those data into our visualizer using the base image because we want to do some quantitative analysis. So here are the results. You can see we're looking at 4 results, and nothing is different except for the amount of SO2 gas that's being let go from the exhaust port. And this is our base image and each subsequent image. So this is at a low concentration, and this is 5 times the concentration, 10 times the concentration, 15 times the concentration. Now, this is a good way to start qualitatively, but if I want to look at the quantitative difference, I may in fact want to show a delta. So what you're looking at in this context is relative to the lowest concentration, what is the net difference for each individual example here. And if you dive in a bit, and I'll turn on, I'm going to zoom in a bit, and for those of you who aren't aware, if you're using Tecplot 360, if you hold the Shift key, you can kind of zoom in and out on the workspace, and that can be convenient like in this case. We'll go ahead and turn on Legend so you can see what those deltas really are, and we'll apply a level skip here. Okay, so that's maybe the image that I'm really interested in, because in this case what we're looking at, or what we want to take advantage of, is what is the net difference in SO2, which you can see these are pretty small values. So if that's my base image, I just want to synchronize that. If I hit synchronize now, I can apply that style information to all the solutions that I'm looking at. It's a very, very easy way to work with data.
Yeah, and you know, a critical process too, to really to see the difference between your results is a critical aspect of really understanding what's going on.
So the quantitative difference, as well as what I've shown you in the qualitative difference, it looks like we're done. The job is complete. We'll go ahead and deposit those into our database. And now our project has more information available, and we can start to look at, for example, let's see here, make sure we're looking at the full. We can then look at, say, northeasterly winds as a function of SO2 concentration. We've just created all these images, whereas before we were looking at, we started with just a bunch of simulation files. Now we can actually start to build out a project. Now, as a start point, you may actually have images to begin with.
Oh, sure. I mean, you could have images that come from actual pictures, for instance, or you may create a bunch of images as part of the process, and of your actual simulation. Your batch job might have their script might include generating some images, but this really gives you a lot of power to look at a large number of cases, and in creating them as images, it allows you to, these could be huge cases. They could be billion cell cases, and it may take a while to generate the images in that case. But once you have them, you can do the comparison very rapidly over a large number of cases.
And so if we wanted to do, say, a qualitative difference here, we can now view those images, apply some labels, just showing what the SO2 concentration, northeasterly wind, and the downwind 50 result. And now we can do that qualitative analysis by doing a diff from the current, and you can see very quickly what the net difference is as you change both the wind and the amount of SO2 gas that is released from the exhaust. So you can see that's kind of an easy way to start. Now there's the concept comes in, all right, well, I want to use this to at least validate my model. So what I'm going to do is go back to that single value filter, and we'll just go back. I'm going to apply a surrogate model to these data, and I'll go ahead and just say I want to use my independent variables as my initial conditions. And if I show that surface now, this is a fit, which shows in effect that for the most part it's linear, which is kind of what we would have expected in terms of integrated SO2. Which is a good way to start. Now this actually might be a good input table, because in principle this is a pretty sparse data set, but based on the data that I have, I really don't need to run the intermediate values of SO2 concentration because they really aren't varying that much.
Right. That That's correct. And now if you saw a big jump somewhere, then you would know you need to go ahead and run some more cases. The other thing here, just to describe the surrogate model a little better, to get any information about what's happening between the points, you really need to have some sort of a model. It could be just a linear model, but in this case, I believe we've actually done is this the response surface?
Yeah, it's quadratic.
So this is a quadratic response surface. So we've actually done a fit of the data in those 3 dimensions, the 3 independent variables, NE, SO2, and SC, I guess. We've done a fit of the data to the Win75 data to those actual points. So this is a quadratic function, and then this is we're just evaluating the surface of that function at a given value of the SE.
And we can also, if we wanted to see how elevation plays into this fit, whereas right now we're just looking at coloring by downwind 50, but we can actually say, hey, let's look at an elevation of 5. So now what we're looking at is the integrated concentration at an elevation of 5 meters off the ground, effectively.
Right.
So this is kind of an interesting way, because remember, this is n-dimensional data, and we can start to see kind of what's going on with the system by evaluating the interdependencies of, say, elevation to location downwind, so to speak. Okay, so let's actually do one additional thing here. So I'm going to go back to my results, and let's just actually grab one result here. We'll view the data. We'll use our start case. If we want to understand the plume migration, well, we really need to look at the plume. And although this is interesting, it isn't in fact a plume, it's just a slice. So I'm going to turn on a plume of SO2 gas at a given concentration, and I'm going to, say, look at a very low concentration. So now what I have is the plume itself, which is cool, because this is ultimately what people like to make decisions on, is, where's that plume going? The tail, so to speak. And some people would call this the dead zone. You don't want to live here.
Right. That's the region where it's above some tolerance. Right?
Exactly.
And so very valuable to see the envelope of that region as you see here with the isosurface.
So I'll quickly save this again as a template. We'll call this actually PL for plume. And I want to evaluate a lot of data at once, but this data is relatively small, but if your data were large, you may want to just look at the surface quantities. So let's actually take advantage of that, and we're going to create some subset information starting with my raw data, and I'm just going to use that plume information, and we'll go ahead and set that up, and it's going to start cranking through, and it's going to generate some surface quantities.
Right, and these files can be, again, this is for very large data generally, and so these files can be substantially smaller, orders of magnitude smaller than the original data file, and yet they contain enough information. It's not just an image, it's actual data, so you can actually rotate it and zoom and look at the details in ways you can't with an image. So
while it's creating the images in the background, we'll take advantage of that time here to go ahead and evaluate, say, the line plots, which would show those integrated quantities. So again, we'll look at, say, northeasterly winds as a function of, or actually maybe SO2 gas is probably a better function, of the downwind 75 integrated amount of SO2 gas. And we'll group these by, say, the SO2 concentration. Or, I'm sorry, we'll group these by northeasterly winds, and we'll sort by SO2 concentration. So you can see we have these little hiccups, and that's because we actually have some southeasterly data that I can move, and if I do, you can see when they're included or when I map them out, or in this case filter them out. And I'll apply my surrogate model, and now what I'm going to want to do is use a single value filter and walk through my different SO2 concentrate, or actually got that backwards, but northeasterly winds. And I'm going to walk through each of the initial conditions here and just look at the fit. And you can see that in this case it's actually quite a good fit, in that there's almost no difference between the integrated quantities and the surrogate model. Okay, it looks like my data has been created. So once I deposit that guy into the database, we'll go ahead and Now we're going to go view data. Now I selected all my data sets. I'm going to look at my new just surface quantity. And it's warning me that, hey, you're selecting a whole bunch of information. You sure you want to do that? And the answer is yeah, sure, because it's relatively small. Remember, these files are already up and rendered. And I will make this a little easier to see by applying a quick tiling of the frames. And there's just make these a little more visible. So now we're looking at an interactive view of the plumes. And this data is very small, so it's quite easy to manipulate and view. So it's kind of nice because you can, when you rotate it, you can kind of get a sense of what those different changes do to the plume. And you can see that at the higher concentration of SO2 gas in this area, you can see what the plume's doing relative to the northeasterly winds.
Yeah, and you can also zoom and or even change some of the styles on the surfaces if you wanted to look at other data.
Sure. So if I decided this actually is an image that I wanted to use for, say, a group meeting, I may want to increase the size of the text. I'll close that real quick and just give this a quick synchronize. And so now what we have is an image that I can take directly out of my visualizer if I choose, which in this case I'm going to just, I guess, copy this directly to the clipboard, and we'll put it into PowerPoint. And let's go ahead and grab all the frames, and we can make this a very high quality image. So right now we'll use this as a bitmap, and we're going to specify just a huge image, say 3,000 points. And it's going to take a second to get that image, and rather than dump it into PowerPoint, I guess I'll just export it out to the desktop. It's fine. Might be easier to get to. Mm-hmm. And we'll go ahead and take a look at this, and we'll call this P, export P. We'll pop down to the desktop, and where'd you go? Oh, there she is. Okay, so here's that image. You can see it's really nice, high quality, crisp image. And you can then zoom in, which I think is this button. I can kind of zoom in to any one of these solutions and kind of walk through. And you can imagine putting this into PowerPoint. So it's kind of a unique way to evaluate a whole system of information. Okay, so we've talked about an optimization study. Mm-hmm. We've talked about running a test case where we just want to understand basic performance, or in this case, something we could use to validate plume migration within a system. The last thing we're going to talk about is taking a look at aero database development and trying to look at surrogate models of data based on performance of an air vehicle.
Yeah, and there's several reasons that people would want to do this, create the aero databases, that is, and do the surrogate models as well. But, you know, they're just to understand the performance of the aircraft, say for a flight mechanics standpoint, stability and control of the aircraft is one obvious use. Another would be for inputs into post-processing, like a flight simulator. You might want a simple surrogate model that could be used to provide your stability derivatives to the flight simulator for the dynamics analysis.
So in this context, thank you, I was just navigating to the result. Mm-hmm. What we're looking at is about 191 solutions, and we're looking at a system where Mach, alpha, and beta were our initial conditions. We have a measure of solution quality, which is the number of iterations. This could be something like residual if you happen to calculate that, but in principle, based on the solution that was used in this case, if it didn't converge after about 150 iterations, it likely wasn't going to converge. Right. Then we have lift coefficient, drag, and pitching moment. So we'll start by evaluating the metadata quickly, and what we're looking at here is Mach, alpha, and we'll look at the lift surface.
So this is a fairly simple database. It just has the flight conditions, Mach, alpha, and beta, but in general you could have a lot more independent variables. You could have, for instance, control positions, and there can be a lot of controls on an aircraft, a minimum of 3 or 4, but you can add a lot more, and various other configurational parameters can come into play as well.
Now, one thing that when you're trying to put together a surrogate model and you're trying to come out with a surface that we're actually going to show you, you can go from the surrogate model actually to a data table that you can provide to stability and control. One thing that you want to do, though, is base it on or try to look at the best possible data. So you can see that if I look at this histogram, most of the results converged in 150 iterations, but you can also see there's some anomalies here. And I can take advantage of that fact, and I can do one of two things. I could say, hey, let's color by that number of iterations, so at least I can see where I have potentially non-converged solutions. And the other thing I can do is get rid of them. I can use my filter to say, well, I really just don't want any solution that did not converge in, say, 150 iterations.
Mm-hmm.
Now, of course, if I had the actual convergence history, I could also bring up the convergence history and look at that as well. This particular example does not have that data. So we'll apply a surrogate model to these data, and we'll go ahead and select the independent variables. And now what we're looking at is a surrogate model of the lift surface. And we'll do the same thing for the drag surface. So in this case, we're looking at Mach alpha and number of iterations. We'll just change that to be drag. So we'll look at the drag surface as well, drag coefficient, and we'll show what the lift coefficient, again, we're looking at n-dimensional data, so now you can understand what lift looks like in the context of the drag. And finally, we're going to show the surrogate model here. So just a quick view here. Now we're actually looking at 2 dimensions of the data. In fact, we could look at pitching moment as well. So there's an easy way to kind of evaluate my system of data.
And this is the surface relative to 2 of your independent variables. Of course, it's not a simple surface in the sense that you see here for 3 dimensions, but it gives you a functional form that you can utilize. And in our case, we're not actually outputting the functional form, but you can output the an array of parameters that can be used by other analysis.
Right, and in principle, we can export the fit as a CSV file. So that it's a pretty common way to export data. It can be used in just about anything, but we're not going to do that just yet. Okay, so you can quickly kind of understand then how the system is performing. And if there's a point that doesn't make sense, you go, golly, there's something about these data points here that I know it's around Mach 1, but maybe it's the formation of shock, maybe something else is going on here. I can start to dive in and say, well, let me look at the images around those data and look at a quick qualitative difference to see, does it make sense? Is it consistent with my engineering intuition? Which in this case, it doesn't look to be. The other thing I might want to do is say, well, gosh, based on that information, I may actually want to dive in and do a quick view of the data themselves. So we can do the same kind of deep dive and now dive in and look at the physics using our physics visualizer.
And the advantage over the images, of course, is that you can zoom and rotate and change the style in ways. And actually, in this case, we have the volume data. You could, if you add the volume data, you could actually add, isosurfaces and string traces.
So in this context, we can also take a look at the quantitative differences between our base case and the other models that we brought in. Of course, you probably would want to know what they are, so you can add those labels. Okay, going back here very quickly, then you can see that it's as a simulation analytics tool, I have the ability then to kind of evaluate these 191 solutions as if it's just a simple project. Now, in this case, I showed you can build a project pretty easily. But there's also, you can use that filtering mechanism even on the table data. So if I start to filter out results, I can look at the results that I'm interested in and just kind of get a subset in a table view. And we're all, as engineers and scientists, this is a very common way to kind of view the information because we're stuck in Excel, whether we like it or not. So this is a good way for people to kind of analyze a system.
Right, and in the end, I mean, the numbers are critical. The pictures are nice and very informative, but you need to know the numbers. So, and you can, from the table view, you can actually launch, view images as well. So you can easily go back and forth between the plots and the table view.
So the last thing we'll do is just look at the CDCL line curve. So we're going to look at, let's see here, make sure I'm in the right area. So we'll look at drag versus lift. And let's go ahead and we'll group these guys by Mach number. And I'm probably going to have to expand. I have enough filters on here, which I think I'm kind of limiting the data too much. Oh, there we go. Great. Okay.
And I think you want to sort by.
Oh, yeah, I'm going to sort by alpha.
Yeah.
Okay. So here are the lift curves for each Mach number. I can then show my surrogate model. So now we're looking at the modeled line. And this is a good opportunity then to walk through the individual Machs or Mach lines and take a look at what's going on. Now, if we find something that just doesn't make sense, if, for example, this is doesn't seem to converge well with the fit, this is an area, again, where because it's all linked together, I can say, well, what's going on with these points? And then go in and view the images, again, do a quick difference to make sure that the data, in fact, makes sense.
Mm-hmm.
So that's, in a nutshell, how you can apply simulation analytics to a number of different cases, ranging from optimization studies to performance prediction. With that, we're going to pop back into PowerPoint, which, let's see if we can do that. And we're going to just move into some Q&A. Quick note on the Q&A, if you raise your hand, we can call on you and try to answer your question, so you can ask it verbally. Or if you choose to, you can go ahead and just type in a question. It looks like we have a few people, so I'll give you a second to type that in. While you're doing that, it would appear that there are people, if you want to, again, look at the simulation analytics white paper, that's available at the link here, as well as if you want to request a vision, or I'm sorry, an evaluation version of Tecplot. So we'll go ahead and open it up to questions. Now, to ask a question, as I said, there's two ways to do that. One way would be to type the questions into the question dialog, and the other would be to raise your hand. So let's start with the first question. There was a question about whether or not we would offer any routines for generic optimization routines. And I think, Scott, the short answer to that is, at this point, no. It's more of a project management tool. But long term, that's something we're going to be looking at adding.
Yeah, certainly long term, that's an analysis that would be important to people. But we feel that in the short term, the more critical thing is to help people really analyze their data and understand their data as a whole. Like you said, the project management.
Okay. There's another question about surrogate models. It seems to be an area people continually ask questions about.
Yeah.
We do have just two models. Is it worth talking about, kind of long-term where we're going with surrogate models in general?
Well, there's a couple of things we want to do. The two we have now are the response surface, second-order response surface, which is really a functional fit, a least square fit of a quadratic equation to the data, the metadata, and kriging, n-dimensional kriging. We want to offer a lot more capabilities there, because we feel this is a critical part of the analytics. So we will be offering more internally, but it's almost certain we'll also have an interface where people can write their own, if they have a method that they've developed over time that they really are confident in. They'll be able to include it into Chorus.
Mm-hmm. There's another question just about what platforms we would support with this tool. Right now we support Windows and Linux, and we intend to support Mac soon for those people who are running on a Mac.
Yep.
I don't know if we're going to have Unix necessarily. Yeah, Linux is probably there. I don't see this coming out on an old IRIX machine.
Yeah, I don't believe that's in the plan at this point. I mean, I suppose anything's possible, but not at this point.
There was a question about performance on large data, since we had talked about that a little bit. We have run some studies, and we looked at a case where we had, I think, on the order of 300 solutions, each of which were a little over 2.5 gigs, so it's about 30 million cells. It's a pretty small file. We were able to go through and create several images, and I think it took on the order of a little over an hour, hour and a half, more or less, to go through and create images. But one thing that was really interesting is by creating the surface quantities, we went from 2-point-something gigabytes to about 14 megabytes. So as a result, in that case, we were able to load in 200 solutions and actually visualize them on the fly, which was pretty cool.
Right, and this is the field data visualization. So this is where you're actually able to rotate and zoom. And yeah, so I mean, this is always an issue, right? Because in computational fluid dynamics and other simulation areas as well, really the size of the problem is expanding with the capabilities of the computers. And so you're always going to have data that feels large. Right. And so that's why we offer these capabilities for the reduced files or the images, so that you can look at all of your entire project at once in something that's fast. If you tried to open all of those in a conventional post-processor and on the volume data, it would be very slow. Yeah.
Let's see, we have time for one more question. So if you have there's still a couple here that haven't been answered, so I'll give you one more minute to ask any additional questions. There was a simple question, I think anyway, on exporting images. I showed you could do it from the visualizer, but you'll be able to do that from the course interface as well. I guess just to answer your question on that. Okay, one additional question about capabilities with data that's not Tecplot. It looks like the data that I showed here today was in Tecplot format. You'll be able to use any format that you can read in Tecplot 360 today could be used with Tecplot cores.
Right. And if you're motivated enough and you have one that currently can't be read in 360, you can write an add-on for it, and then you'd still be able to read it in Chorus. So yeah, they're all supported.
Okay. Let's see. White paper link fails. Yes, I was just told that, in fact, we'll send that out to you because it looks like there was a typo in that. So don't worry, we'll send you the link post-haste here. Thank you again. Any additional questions, we'll probably answer by email. But again, I wanted to thank Scott Imlay for joining me here this morning, and thank all of you for joining us in what we feel is an interesting exploration of simulation analytics.
Yeah, my pleasure. Have a good day, everyone.
Thank you.